Okay, we continue, and our next presenter is Bruce Silver. And many people know Bruce as probably one of the best trainer in decision intelligence area, including BPM and DMN. And Bruce also authors of several books. And I don't know exact number, but probably you trained more than 1,000 or maybe a few thousand people, and they all became users of these technologies, right, Bruce?
Right.
Uh, Right. And so if somebody wants to get good training on DMN or BPMN, Bruce is the right person to do it. But today, Bruce will demonstrate us how he used field language in DMN to solve Sudoku problems. And it's kind of interesting. It's not a production level environment, but we can learn a lot how to use field expressions to implement quite complex algorithms. Okay, Bruce, let's go
Thank
forward.
you, Jacob. Yes, this presentation concerns the application of DMN to something many of you are familiar with, a logic puzzle Sudoku. My role in the decision management world, as Jacob said, has been mostly helping business users create executable DMN models through training and engagement work, complex models that solve real problems. And DMN was actually designed for non-programmers, in particular by its standardized tables called boxed expressions and its expression language field. But for whatever reasons, these features of DMN have not received the love that they deserve within the decision management community. But I continue to evangelize their power and their accessibility to non-programmers. So here's something I did just for fun that illustrates that. Using DMN to create a solver helper app for Sudoku. The logic is complex, but it can be handled just using field and boxed expressions. I learned a lot doing it, and I'd like to share that with you today. So for those who don't know, Sudoku is a logic puzzle that had its peak of popularity around 10 years ago. And I expect many of you are familiar with it and maybe even still a fan. For those unfamiliar, the puzzle is a 9x9 grid in which a couple dozen cells are populated with numbers from 1 to 9. And to solve it, you need to fill all the cells with numbers so that each row, each column, and each 3x3 block contains exactly one instance of each number. In addition, a proper Sudoku must have exactly one solution. You can find these puzzles in newspapers, airline magazines, puzzle books, iPhone apps, where they're usually rated with a degree of difficulty like easy, moderate, hard, or killer hard. But the basis for these ratings is never stated. The rules and objective of Sudoku are clear, so it's not surprising that Sudokus can be solved automatically in software. And in fact, a large number of Sudoku solver programs have been developed using a variety of approaches, ranging from those based on constraints to simultaneous linear equations to Knuth's exact cover and dancing links algorithm, and of course, backtracking, a brute force approach where the app guesses a value and backtracks if it leads to a dead end. But none of those methods do it the way a human solves the puzzle, which is to look for patterns in the possibility set or post set of each unsolved cell, and using those patterns to further reduce the possibilities until there's only one poset value for the cell, which then becomes the cell value. I wanted to create a solver using this pattern finding approach with DMN. I'm hampered by the fact that I myself am not a programmer, but I am able to use DMN as a general purpose, model-driven, low-code language. And in the course of doing so, I learned a lot about feel, a lot about Sudoku patterns, and a bit about the Sudoku puzzles that you find in newspapers, books, and apps, which I'll share with you today. First, I'll discuss the patterns, and after that, how we deal with them in DMN. The 6 patterns listed on the left side here are what I call the easy patterns, meaning they are easy to detect visually. Scanning is what most people do first. Look for the only cell in a row, column, or block that could contain a certain value. Based on eliminating that possibility, if it is the value of some other cell in the same row, column, or block. For example, here, looking at block 3, that's the top on the right, the 8s in columns 8 and 9 eliminate those columns as possible 8s, leaving only one cell possible, row 1, column 7, where I've entered the red 8. With scanning, you don't need to write down the post sets for each open cell. With all the other patterns, you do. Once you do record all the post sets, look for naked singles. Those are cells where the post set contains only one value. That becomes the cell value, and you can then remove that value from the post sets of all other cells in the same row, column, and block. Here I haven't written down the post sets, but looking at row 1, column 9, and mentally eliminating post set values matching the entered cell values of all other cells in its row, column, and block, we see that it allows just a single post set value, 1. So that becomes the cell value. That's a naked single. Hidden singles are like scanning, but they reference the recorded post sets, not the cell values. A hidden single is the only cell in a row, column, or block that contains a particular value in its post set. In the grid here, you see the output of my helper app, where the post sets are recorded as the lists of numbers enclosed in brackets. Note here that in column 5, the only cell with 4 in its post set is row 2, so that is a hidden single. We thus set the value of row 2, column 5 to 4, and we can eliminate 4 from the post sets of all other cells in row 2 or block 2. Only scanning naked singles and hidden singles enter cell values. All the other patterns just affect the post sets. Naked pairs are easy to see. 2 cells in the same row, column, or block that contain the same 2-value post set. Here there are 2. 1 and 6 in row 1, and 6 and 7 in row 3, here highlighted in green. When you find a naked pair, you can remove those values from the post sets of all other cells in the row, column, or block. Those are the post set values here highlighted in yellow. Naked triples are similar. 3 cells where the distinct values of all 3 post sets combined totals 3. Here, for example, 5, 8, and 9 in row 5. You can then remove 5, 8, and 9 from the post sets of all other cells in that row. And naked quads work the same way, but with 4 cells and 4 values. So those are the easy patterns. Actually, to solve the puzzles in most books, airline magazines, and iPhone apps, those are the only ones that you need. The only ones. But for hardcore Sudoku fans, that's too easy. There are actually many harder patterns, such as those you see listed on the right, discussed on the hardcore Sudoku websites. Not only are these other patterns, or what the screenshot calls strategies, harder to see, they're often even hard to understand. Some of them I've found difficult to follow even after reading the explanation multiple times. But they occur only rarely, And in the table on the left, I listed just the 6 harder patterns that I use. I began this project with the intent of using DMN to find these 6 patterns automatically. A hidden pair means there are only 2 cells in a row, column, or block that contain either of 2 poset values. They're hard to see. Here, the pair 2 and 4 in column 3, rows 4 and 5 is hidden. Since those are the only cells in column 3 with 2 or 4 in the poset, one must be a 2 and the other a 4. So you can remove any poset values other than 2 or 4 from those cells. Similarly, the pair 3 and 7 in row 5 is hidden, as is the 3 and 7 in column 7. Again, you can remove the any poset values other than 3 or 7 from the hidden pair cells. Hidden triples work the same way, and they're even harder to see. Here we have 2, 5, and 6 in row 1, highlighted in green, meaning those are the only 3 cells in row 1 with 2, 5, or 6 in the poset. So we can remove any other poset values from those cells, the values highlighted in yellow. And once we do that, another hidden triple appears, 4, 7, and 8 in column 9. And again, we can remove the other poset values from those cells, the ones highlighted in yellow. So as you see, we are gradually reducing the number of poset values in the cells until we get a naked single or hidden single, which then sets the value of that cell. Locked values is a pattern I was unaware of when I started this project. Locked values occur when all the cells in a certain block containing some poset value are in the same row or column. For example, here in block 3, all the 3s are in row 2. That means the only possible cells in row 2 with value 3 must be in block 3. So you can remove 3 from the poset of all other cells in that row, meaning columns 1, 2, and 3, the cells here highlighted in yellow. Similarly, you have lock value 2 in block 8, row 7, so you can eliminate poset value 2 from any other cell in row 7. Here, column 2 highlighted in yellow again. Not shown here, but you also can have locked values when all the cells in a row or column containing some value are in the same block. In that case, you can remove that value from all other cells in the block. An X-wing involves 4 cells in a rectangle in which either the pair of cells in each X-wing row are the only ones in that row with some poset value, or the pair in each X-wing column are the only ones in that column with some poset value. First type we call X-wing in rows, the second type X-wing in columns. So here we see an X-wing in rows for value 7 labeled A, B, C, and D. Those are the cells shaded orange. Cells A and B are the only ones in row 2 with 7 in the poset, and C and D are the only ones in row 6 with 7 in the poset. So if A is 7, then B and C are not 7, and D must be a 7. And if A is not 7, then B and C must be a 7. So that means that either A or C must be a 7, and either B or D must be a 7. Thus, no other cells in columns 4 and 8 can be a 7. So you can remove 7 from the posets. Those are the 7s shaded here in yellow. This is the most common form of an X-wing, but actually there are more variants. An XY wing involves 3 cells, each with 2 values in the poset. The hinge cell, here shown in orange, is linked to 2 wing cells, one in the same row or column as the hinge cell and sharing one of the poset values, and the other in the same block as the hinge cell sharing the other poset value. And the other poset value of the wing cells, the one not shared with the hinge cell, must be the same. So remember, when a person is solving this puzzle from the newspaper Sudoku app, he or she is staring at all these posets and trying to detect such a pattern visually. It is very difficult. So here the hinge cell poset is 3 and 8. If the cell value here is 3, then row 9, column 2 must be a 4. And if the hinge cell is an 8, row 2, column 3 must be a 4. So either way, we can remove 4 from the poset of any cells that are both in block 8 and column 3. So that is row 8, column 3, the value highlighted in yellow. Yes, searching for these patterns by eye can make your head spin. And these are just the easiest of the hard patterns. Just a minute here. All right, the last pattern I'm going to show you, called unique rectangle, arises from the requirement that there must be exactly one solution to the puzzle. Applying this pattern eliminates this possibility, that eliminates the possibility that there are two solutions. In a unique rectangle, we have 4 cells arranged in a rectangle. 3 of the 4 cells, here shaded in yellow, have identical pairs of poset values, 2 and 4. And the 4th one, shaded orange, has that pair plus some others. The 4 cells must lie in 2 separate blocks, not 4. If the value of the orange cell is either of the shared poset values, 2 or 9, I think I said the identical pairs of poset values are 2 and 4, they're 2 and 9. If the value of the orange cell is either of the shared poset values 2 or 9, this is called a deadly pattern, since it leads to 2 possible solutions to the puzzle. Thus, the poset of the orange cell cannot contain 2 or 9, so you can remove them. This is just one of 6 or 7 variants of the unique rectangle pattern, but they all follow the same basic logic. Okay, so we want to be able to find and fix all of those patterns automatically in the solver. So let's look at the DMN. So here is the DRD for the solver app. It's a chain of 12 decisions, S1 through S12, each processing a single pattern, the easy ones and the 6 hard ones. The DMN model is going to search for those patterns in some sequence, and when it finds the pattern, make the appropriate changes to the grid, eliminating the poset values, and in the case of singles, assigning the cell value. To the right of each decision, S1 to S12, is another decision that simply formats the grid so that you can view the values and the posets detected so far. So the whole DRD is hard to see in that slide. So here is just the bottom part of it magnified a bit. The input data S is a 9x9 table for convenience imported from Excel. Decision S1 reformats that to an 81 row table used in all the internal computations, 1 table row for each cell in the 9x9 grid. Each subsequent decision in the chain takes as its input the output of the previous decision and looks for one particular pattern, one of those we've discussed. And if it finds the pattern, it logs it. Then it applies the action, which involves removing some poset values from various cells. In order to visualize the result, a shared BKM called FSOut, you see here, maps the output of each decision in the chain to a 9x9 grid for display. In this DMN model, we've defined 12 decision services, each one a single decision, S1 through S12, plus its out decision as the outputs and its immediate information requirement as the input. Then we execute these decision services in a decision flow process, one at a time, that loops back to the S2 service whenever a pattern is found and the grid is updated. So I'm not going to drill down in depth on the field here, but if you're a field nerd, I believe it is worth studying. Each decision is modeled as a context, and the first context entry is a function definition, taking the cells of a single row, column, or block as its parameter and searching for the pattern. If the pattern is found, it returns a structure with the pattern values and its location, or null if the pattern is not found. Usually it returns null, so we need to filter those out of the function result. The rest of the function definition is complicated and depends on the details of the pattern, but it's typically something like this. If some pretest to eliminate iterating over empty lists or null is satisfied, then perform a double or triple iteration. We need double or triple iterations because the parameter contains 9 cells, and each cell could contain up to 9 posit values, and sometimes we're looking for a combination of 2, 3, or 4 cells. Remember, all we're doing here is searching for some pattern in a single row, column, or block. The iteration executes a conditional expression, testing a complex pattern condition, and if found, it generates a structured value. In order to return a structure from a single complex condition in a literal expression, we output a context literal, which is a list of key value pairs enclosed in braces, a JSON-like notation, or else null if not found. That's valid field, although I had not previously used context literals. Then we need to filter the whole iteration with item not equals null, since just 1 or 2 items in the iteration typically will return a non-null value. So here you see the function definition looking for hidden pairs, magnified. I've magnified one of those expressions so you can see it more easily. You can see the context literal in braces there. This is just the first context entry, which is used to find the pattern in a single row, column, or block. In subsequent context entries, we still need to iterate this over all the rows, columns, and blocks. For each discovered pattern, figure out which cells I need to update, log the action, and apply the updates. I won't bore you with the details, but if you're interested in this kind of feel on steroids, I will try to make the model available to you. Just to return to another little known feature of feel from the previous slide, multiple iteration. That's a cool capability. You can iterate over multiple indices in a single expression, and the scope of one index may depend on a previous one. So as you see here, this example taken from the decision looking for a unique rectangle, we have a triple iteration where the scope of index n depends on the previous index m. Here we're just trying to capture all combinations of poset values m and n, where m is always less than n in all rows. That's index r. So we need a triple iteration. These multiple iterations generate a single list, not a list of lists or lists of lists of lists. That's very handy. I mentioned that while we have a single DRD, we're going to execute it one decision at a time using a BPMN process with decision tasks invoking our DMN decision services one at a time. When a pattern is found and some poset is then reduced, we loop back to S2 to look for naked singles and continue on from there until the puzzle is solved. This might not be the best from a performance standpoint, but it's the most straightforward for me. So let me magnify the first part of the decision flow of the solver app in BPMN. Each decision task in BPMN, those are the boxes with the table icon, invokes one DMN decision service. Remember, that's one decision S1 through S12 plus its associated out decision, which just formats the grid for display. The decision task outputs to a process variable, shown in the diagram as data objects. Those are the dog-eared page icons. Each script task, those are the boxes with the scroll icon, simply maps between process variables and task variables. On the Tricitech platform, that mapping is a field literal expression. So if you know feel, you can do executable BPMN as well without programming. The dotted arrows called data associations indicate the data mappings. If a decision task finds a pattern and changes the posets in any way, the flow then loops back to S2, naked singles, using the gateways, the diamond shapes. So you see all those sequence flows going back into S2 and all those data associations into data object S2N, the input for S2. It's not fast. Execution can take 30 seconds for a simple puzzle to a few minutes for a hard one. Some of that is DMN, which isn't particularly fast. Some is the fact that I'm not a programmer and I don't know how to optimize the logic for performance. Perhaps one of you, maybe Octavian, could do a better job with that. So let's try it out. We can copy a puzzle from some puzzle source into a 9x9 grid. For convenience in Excel, with Tricitech, it's easier to save them and enter them in Excel and then import them. So now using the test feature of Tricitech Workflow Modeler, remember we're using BPMN here, which executes the DMN, we can import that Excel file, that 9x9 grid, as our process data input. Excel import is the icon circled in red there in the bottom left, and then submit. The process then runs to completion, either solving the puzzle, as it did here, or giving up. When the process completes, the 9x9 grid S out displays the cell values along with the list of logged patterns found. Naked singles are not logged by my app. A nice feature of Tricitech Workflow Modeler in test mode is that the paths followed in the process, all those loopbacks, are highlighted in the diagram here in green. Might be hard to see in the Teams. All right, so now we need a source of puzzles. I started with a book from the famous puzzle master Will Shortz. The puzzles in this book are typical of those you find in the newspaper Sudoku apps. The puzzles are rated from easy to moderate, demanding, very challenging, even mind-melting. But those ratings are just to make you feel smart, because as you see here from the Excel table on the right, they all can be solved using only the easy patterns. In this Excel table, I've listed the results of 15 of the puzzles from the book with Will Shortz's difficulty rating and a list of the patterns found with a count of each pattern found in parentheses. I mentioned earlier that naked singles when the poset contains just a single value, those are not logged. So you see that the first 26 puzzles, including the first one called moderate, only required naked singles, solved but nothing logged. The fact that even the supposedly mind-melting puzzles use only the easy patterns was a total surprise to me, as my original goal for the app was to help users in looking for the hard patterns. But just to find examples of the hard patterns, you can't rely on conventional Sudoku puzzles that you find in books like this, or Sudoku apps or the daily newspaper. To find a source of the hard patterns, you need to look for books and websites focused on those. So here's one, the book I used to learn Sudoku 10 years ago from Peter Gordon. This book explains the patterns, how to find them. And so it provides examples of some of the harder patterns and puzzles. In order to fully test my model, I needed to use puzzles from this book, as well as some I found from Sudoku websites. Here, the Excel table shows examples from this book with a chapter name specific to a type of pattern. And again, the patterns found by my app. You can see they include several of the harder patterns. But notice none of them include hidden pairs or hidden triples. In fact, neither the shorts book nor this book even mentions hidden pairs or triples, although they are discussed on Sudoku websites. But even using examples that I found there, because my BPMN only looks for the hard patterns after exhausting all the easy ones, the hidden pair examples on those websites were solved in my app using only the easy patterns. So I'm guessing that hidden candidate patterns are actually quite rare. Maybe don't exist at all if you always check for the easy patterns first. So once I had taken the Solver app as far as I wanted to go, I turned my attention to the Helper app. And that's because puzzle users, that's you, you know this, don't actually want the solution. It's in the back of the book already. They just want some help in solving it. And two main areas would be especially helpful. One, recording the initial post sets for each empty cell. With manual solving, that's quite tedious, and it's the most error-prone part of the effort. And two, hints to look for a particular pattern if you get stuck. The Helper app would do those two things. The only difference from the Solver app is the insertion of a user task, here modeled as a call activity, so it could be modeled as a screen flow, a reusable subprocess of user tasks that let the user opt out of seeing the hint. But in this version, I just show the hint. So now, after finding a pattern, but before updating the grid, the user task displays the grid and the hint. Unlike the solver, which can be run from the modeling environment, to run the Helper app, you need to deploy the model, which on Trisotech is just a single mouse click. So here I've uploaded a puzzle and run it. And it stops at the first user task, which then displays the grid S out, which includes the post sets for each empty cell, a list enclosed in brackets. So if you see just a number, that's the cell value. And if you see numbers enclosed in brackets, those are the post sets. So you can print out this grid, which now has all the post sets enclosed in brackets, and proceed to solve the rest on paper. That was the first Helper objective, write down the starting post sets. It also provides the first hint, which is to look for 3 hidden singles, and tells you where they are. Remember, I said you can tweak the screen flow to not show the hint if you want. So let's use the hint, the 3 hidden singles. Remember, that's a row, column, or block in which only one cell contains a particular poset value. So you can eliminate that value from the posets of all other cells in that row, column, or block. And here I've highlighted the 3 hidden singles in green and the corresponding poset values to be removed in orange. Now, in the app, if you click Continue, it will update the grid, removing the orange poset values and looping back to S2 service and continuing until the next user task. So we do that. And now you notice that the values marked in orange from the hint, shown here at the top screenshot, are now gone from the new posets, shown at the bottom, demonstrating that the helper app is working as it should. Okay, so what can you take away from all this? First, that it is possible for a non-programmer to build a reasonably powerful Sudoku solver app using DMN and BPMN, although performance is relatively slow. And I think by extension, my intention was to show that a non-programmer can build reasonably complex logic solutions for the real work. Second, that the supposedly hard puzzles in Sudoku books and apps are actually easy, meaning you can solve them with only the 6 easy patterns. You have to go to special books and special websites, the ones that teach the hard patterns, to find the really hard Sudokus. And third, I thought I knew the patterns, but there are several I was previously unaware of, such as the hidden pairs and triples and locked values. So now I am a better human solver as well. And most important, I think, from the standpoint of DecisionCAMP, we see that DMN is quite powerful. It's not just decision tables. As I said at the start, field and box expressions deserve much more love than they've received. I don't know if Gary Hallmark is here today. He was on the panel yesterday. He's the inventor of field, and I think we all owe him a great debt of gratitude for that language.
Yeah, Gary is here.
He is here?
He's listening. He is listening.
Okay. Thank you, Gary. I think you did us all a great service. So the field in this project was very interesting. The field in this project was very interesting. I learned a lot from creating the models. So if you are inclined to take a closer look at them, email me at bruce@brsilver.com, and I will try to get you some access to them. Ideally, you can improve on them. New patterns, faster implementations, whatever. I look forward to your improvements. And thank you for your attention, and I'm available now for questions, if there are any.
Thank you, Bruce. I think it was a tough job to do it. And thank you very much for sharing this. Any questions?
Hey, Bruce, great presentation. I wonder, do you think it's possible to do a brute force solver that does backtracking? Maybe using the for loop with the partial so that you can see what it's done so far. And I mean, I guess you would have to have
I think it would be possible. I think it would be possible. So basically, the way backtracking works is it looks for the really simple patterns, like the naked singles and probably hidden singles, and then beyond that, it just guesses where there's like a poset of 2 values, and it guesses one of them. And this, from what I've read, is in Java at least the fastest way. The fastest solvers use that. So I imagine it would be possible, and probably faster than this one, to do it that way. It wasn't as interesting to me personally, because I'm like a Sudoku solver. I wanted to do it the way I think about it, but that might be a good way to do it. I think it would be possible. Definitely. Yeah. So, well, Gary, you might not like this, but I think it might be possible, since you don't know how many iterations you need to do, you might need to use recursion, which, as you know, works, but you've never liked it. So that's a warning on that.
Well, no, I love it, but I don't like teaching it to business people so much.
Right. Well, it has the risk of blowing up with infinite loops, and that's in a shared tenant environment. That's
Exactly.
not so good. So
So we always say it's pretty hard to write an infinite loop. I mean, I think if you stick to the spec, it's impossible. But if you go back to the good old days of production rule engines, it was almost impossible not to write an infinite loop. So just one controversial point here, not because why not? So I think the fastest way to do this without coding is just to ask ChatGPT, which I just did, to give me a Python program that solves Sudoku. And just with that prompt, it generates a short program. Now I haven't run it to try to see if it actually works or not, but it actually generates backtracking. So then I ask it, well, can you do something without backtracking? And it kind of thinks for a second, and it says, well, I can do part of it. You'll have to dig into things like pairs and hidden pairs and things like that. So it kind of gives a shorter version of what you had that just does the easy cases, and then it says, and if that doesn't work, then just fall back to the backtracking case.
very,
So
very interesting.
Kind of interesting.
Yeah. Well, I knew somebody was going to say, well, couldn't you just ask ChatGPT to write a solver program? And you probably could. And as you said, you can. But my goal was really just to demonstrate the power of feel and box expressions, which it does. So.
Yeah, I just did this with Copilot. I put it there. You can see. I just want to make one comment that it's not this is example where it's not necessarily about problem solving and about different techniques where Copilot and LLMs will work probably perfectly. You can see, for example, I just tried and I asked Copilot if they can solve any complexity, not the simple Sudoku, and it says, just give it to me and I will solve. So I'm not sure,
okay.
But we will see. You can try yourself. But I just want to make a point. Alan is not here, but he would probably tell that it's not always about just problem solving. We should think about humanity. I can tell you just brief story. I told this before Bruce. My mom, I introduced my mom to Sudoku when she was 85. And she got hooked on this, and it make her life much better. She was a single woman at that time, and by 90, she started to show me her own patterns she invented without any tools. And it was so important for her. And when she was 94, she told me, how can I live without this? Because I cannot hold the pen anymore. And of course, she could not use computers at that time already. But it definitely helped humans to not only with Alzheimer or other problems, but it's just really not always about the best technology. It's about us humans, and we should remember this, whatever new shiny thing is around. Okay, anyway, I think it's a really good proof about power of DMN, complex field expressions. And if we don't have any more questions, Bruce, thank you very much for this presentation.
Okay, thank you.
Yeah, thanks.
Okay, let me stop recording.